right. We are going to continue talking about energy today, and we're going to first let's just review what we know so far. In order to um, transfer energy into out of a system, we have to do work, and work is equal to the force that you apply times the displacement. And remember that these have to be parallel to each other. So sometimes when we're dealing with, pulling something with a rope at an angle or pushing something at an angle, we'll have to find the horizontal component of the force and multiply it by the horizontal distance that we're moving it. And so sometimes you'll see that equation as Fx cosine theta, where theta is the angle between the force that you're pushing with at an angle and the displacement vector. We also talked about kinetic energy, which is the energy due to motion, which is 1/2 mv squared. And we said that in order to make something change its kinetic energy, you have to do work on it. And that's called the work change in kinetic energy theorem, which just says that Fx equals the final kinetic energy, 1/2 mvf squared, minus the initial kinetic energy of the system. And what's nice about this formula is that now we can kind of move away from our kinematics equations and our F equals ma equations, and we can solve similar problems that involve both of those with just one formula. So if we know the change in kinetic energy and how far the object moves, we can figure out the average force exerted on it. Or if we know how much work is done on the system, we can figure out the change in kinetic energy and the final speed of it. So these are kind of powerful relationships. The other thing to remember is that work and energy are scalar values. They have no positive or negative direction. They don't have to worry about giving a polar heading or having components to them. But you can have a positive change in energy or a negative change in energy when you gain that type of energy or you lose that type of energy. So the other type of energy that we're going to talk about today is potential energy. And there are two types. There's gravitational potential energy, and the symbol for that's going to be UG. And instead of using a P, we use a U because when we talk about momentum later on, the symbol for momentum is a P. And so there's gravitational potential energy, which is due to position, relative change in position. So, for example, lifting an object a certain height increases the amount of stored gravitational potential energy. And another type of potential energy is the potential energy in a spring that's due to elasticity. So we'll call that UE for elasticity. And we will be talking a little bit about springs, and we'll talk about the stiffness or the spring constant of a spring and the force needed to stretch it in the stretch. But we'll also relate that to how much potential elastic energy it has stored in it when you stretch it out or you squeeze it. All right, so let's move and let's talk about gravitational potential energy. So we've talked about this before. If we lift an object up a height, and let's just assume that we lift it with the bare minimum force, which is just enough force to overcome its weight. So if we lift it up with a force that's equal to its weight, and I'll just go ahead and draw the vector diagram here. The actual force that's doing the lifting is going to be that applied force. And we're going to lift it a certain height, right? And if we were to find the work to lift it, the work to lift it against gravity would just be the force that we applied to it times that change in height, or its weight times its change in height. So when we do lift it up to that point, to whatever that height is, we now have given it some potential energy because If we let go of it, gravity will make it lose that potential energy and turn it into kinetic energy. So the basic formula for finding the potential energy at any point in that traverse from a reference point, where there's no height to where there is height. So anywhere along this line, I can find the potential energy by just taking the weight and multiplying it by the height at that location. We're not going to worry about putting in the negative for 9.8 because our directions are going to be kind of assumed here. We're looking at the absolute value of this information. So gravity is 9.8 meters per second squared. Your mass needs to be in kilograms. Your height needs to be in meters. And that's going to give you a kilogram times a meter per second squared times a meter, or a kilogram meter squared all over second squared, which is indeed a joule. So remember, the symbol is going to be UG for gravitational potential energy, and the unit is going to be joules. So let's look at an example. A 50-kilogram girl falls 100 meters. How much potential energy did she lose? So let's just draw a diagram here. So we've got 100 meters here at this location, and she's going to fall down to a height of 0. So if she starts here at point A and she ends up at point B, her change in potential energy is going to be the potential energy at B minus whatever she started out with, the potential energy at I, because the change is always the final minus the initial. Well, since potential energy at any point is mgh, if h is 0, then the potential energy at B is going to be 0, right? Because she is not. She's got some reference point. And it's okay for you to assign the lowest point in the particular scenario as the reference point, because we really want to look at the change in height relative to some starting point. So it makes sense to use the ground as 0 and then the 100-meter high cliff as the other position. So this is going to be 0, and this is going to be negative mg whatever h at A is. So notice that this is going to be a negative change. It means we're losing potential energy because as height goes down, potential energy goes down. It's a direct relationship. So we're going to lose 50 kilograms times 100 meters times 9.8 meters per second squared. And that's going to give us, 5,000 times 98, or 9.8, and that's going to give us a change of negative 4.9 e to the 4 joules. So if I make this kilojoules, that would be negative 49 e to the 3 joules, or negative 49 kilojoules. So we're losing that much potential energy. So ask yourself, we don't just lose energy, it has to turn into something. Well, the gravitational force is doing work on this, right? It's causing there to be a transfer of one energy into another. And as she loses height, and she loses that 49 kilojoules of potential energy, she is gaining that amount of kinetic energy. So keep that kind of in the back of your mind, because you cannot create energy from nothing, right? And you can't lose it, can't just disappear. So if you had a certain if you had 49,000 joules of potential energy at point A, and then all of a sudden at point B you don't have any, it had to turn into something. And assuming there's no friction in the system, it turned into kinetic energy. Well, what about elastic potential energy? So elastic potential energy has to do with how far you stretch it and how stiff it is. So let's talk a little bit about the basics of elasticity. So with a spring, think about a rubber band. When you stretch a rubber band, it gets harder and harder. And that force of the rubber band's pulling back on you. So you might be pulling that rubber band. So here's your rubber band, right? It's kind of flimsy. And then you pull it taut, right? You are pulling on it, and the rubber band pulls back equal and opposite on you. And that K stands for the elasticity constant or the force constant. So this force that's due to how stiff that rubber band is, the force constant, the spring constant, the elasticity constant, there's a lot of different names for it. That force changes. It gets bigger and bigger as you stretch it because it's directly proportional to the stretch. The equation that talks about that is that force of the spring on you is opposite your direction. That's why there's a negative here. It's equal to K times X. X is the stretch. So if you stretched it a meter or you stretched it 10 centimeters, that would be what you plug in for X. And K is the force or spring constant, and it's like the density of something, right? It's a property of the spring or the elastic material, and you would be given it, or you could determine it because it's measured in newtons per meter. It is something that would be given to you. So I might say, for example, the spring constant is 20 newtons per meter. That means that it takes 20 newtons to stretch it 1 meter. Or I might tell you it takes 100 newtons to stretch it half a meter. So if you wanted to find K, you would just take 100 and divide it by a half, and the spring constant would be 200 newtons per meter. So this is something that either you give up, you look up, or you can calculate really easily. And so it's not surprising that the stiffness of the spring increases with that constant. So the higher that constant is, the higher the stiffness is, right? It's more stiffer, right? It's more stiff. Also, think about that. The more you pull that rubber band, the less you want to let go of it because it's going to hurt when it snaps back at you because it's going to gain a lot of kinetic energy. So the elastic energy is proportional to that spring constant, and it actually is proportional to the stretch squared. So like if you stretch it 1 meter and then you stretch it 2 meters, you're going to have 4 times, not just 2 times as much elastic energy, potential energy stored in it, but 4 times as much, which means that when you let go of it, you have 4 times as much energy turning into kinetic energy, which makes it travel faster and it hurts more. And then there's a constant here, 1/2. So the more this is stretched, the more potential energy it has. So let's look at an example of that. So let's say that you have a spring with a constant of 30 newton meters and it's stretched 30 centimeters. How much potential energy does it gain? So here's our spring, just at rest. Okay. I'm just going to imagine that this is a hand. Okay. And then we're going to stretch it 30 centimeters. All right. And we know that K is 1/2 K. K is given to us 300 newtons per meter. So first of all, everything needs to be in standard units. So if K is in newtons per meter, then our stretch needs to be in meters. And 30 centimeters is 30 times 10 to the negative 2 meters, or 30 hundredths of a meter, 0.30 meters. So we're going to plug that in for X. Now, when it was at point A, X was 0. When it's stretched out to point B, X is 0.30 meters. So if we want to find how much potential energy it gains, we're really finding the change in potential energy as it goes from A to B, which is going to be UB minus UA. UB is going to be 1/2 of 300 newtons per meter times 0.30 meters squared minus 0, because X was 0 when it was at rest, not stretched at all. So that's going to give us 0.3 squared times 1/2 of 300, and that should give us 13.5 joules of energy. If I double X, so that I stretch it 0.60 meters, the elastic energy is proportional to X squared. So if I double it, right, then UE is going to be 4 times bigger. So it would be 4 times that. If I triple it, it'll be 9 times that. If I quadruple it, it'll be 16 times bigger than 13.5.